Hello everyone. So today should be our last video in 7.1. I'm going to try to keep this one short because I know the last couple videos were a little long and they're over 30 minutes. So the first thing I want to talk to you about today is a kind of formal definition on how to write an iterated integral. Okay. Now that we have worked on iterated integral for quite a little bit, and you kind of have an idea as to how the different aspect or different part of the iterated integral, how it work with the Riemann integral and things like that. Now maybe it's better to finally define it. So let's say we're given a function f that maps from Rn to R, and we're going to let B be a closed regions in Rn. Let's say let B be defined by the following inequality. So here's the important part, is how we set up this set of inequality that give us a way to describe the regions B and therefore transform into our iterated integral. So this is how it works. In this case, I'm going to say B is defined through this set of inequality. So starting from the bottom, I'm going to say x sub 1 is gap between A1 and B1. X sub 2 is gap between the function A1 of x1 and A2 of x1 and B2 of x1. And then x sub 3 is gap between A3 of x1, x2 and B3 of x1, x2. And this pattern continue on to the last variable A sub n, which gap between A sub n of x1, x2, to... Alright, let's see if I can squeeze this in. Oh, you know what? I'm going to just make more room. I don't want to squeeze it in. A sub n of x1, x2, to xn minus 1 to B sub n of x1, x2, to x sub n minus 1. So that's how the set of inequality works. It starts from the last variable that you want to use, and it can get between two functions that are using all of the variable from underneath it. And then work your way all the way down to the first variable, which has to be get between two constants. Now, I'm simply listing regions B by describing using all the variables that's involved, or n, so the n variable, and just listing them in order from x sub n all the way down to x sub 1. But you can actually reverse and change them. But the problem is when you reverse and change them, the way the function have to be used to describe each variable has to be the same. It has to use all of the variable, or allow to use up to all the variable underneath it. Okay, so the lower you put an inequality, the less variable that you can use in the list. And eventually would go from the top inequality, which can use the most number of variable, down to the bottom inequality where you can only use one pair of constant and no variable. So that's how the description works. And when you have B described by this following inequality, then we can define the double Riemann Riemann integral over B, f of vector x dv, would basically equal to integral from A1 to B1, integral A sub 2 of x1 to B sub 2 of x1, to integral A sub 3 of x1, x2, to B sub 3 of x1, x2, all the way to the integral from A sub n, x1, x2, to A x sub n minus 1, to B sub n of x1, x2, to x sub n minus 1, of the function f of vector x And then now, because of the way I'm writing out the limits, I have to establish the order dx sub n minus 1 dot 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 to dx sub 1. So that's how you properly set up your integral, iterated integral. And look at the way the limit is. The limit has a definite progression from the innermost limit, which have all the variable. We could have potentially all the variable on the outside integral. And then each layer, you are using one less variable in your limits, one less integration, one less differential, until you work all the way to the outermost integral, where the only constant as the limits. So that's how a proper setup iterated integral work. Now, I know that might look confusing to understand, but show you some examples set up for a specific type of function. So therefore, let's say for function f of xy, or for function f that map from R2 to R. This type of function have basically two ways to set up the integral. There are basically two ways to set up your iterated integral. One of them is this way, is that integral, double Riemann integral b of f of xy dA would equal to a1 to b1, and then a2 of x to b2 of x, f of xy dy dx. And this way would basically describe the regions B using these two inequality. A2 of x for y, b2 of x, and then x gap between a1 and b1. So that's one way to do it. A second way is to describe it this way. Now, it might seem like, oh, that's the same, but no, notice what happened to the inside. See, the outside would be the same, be using constant. And the constant could be different value, but it will have to be two different constant. One we'll call it A1 and B1. But the inside one, where you can now use variable, then it's a little different. So this way would describe B using these two inequality. And of course, remember, in these two descriptions, the A1 and B1 might be different numbers because they represent different variable. So they very unlikely being the same numbers, because what worked for X may not be the same for Y, obviously. So that's for function map from R2 to R. Now, notice that the problem here is the following. Some of you probably already recognize the issue. The more independent variable there is, the more ways to arrange the differential. See, for two independent variable, meaning two differential dx and dy, they can either do dx, dy, or dy, dx, and that's it. But for function that map into R3 to R1, which would probably be better for you to see how the limits work out, but it's definitely require a lot more writing, because for function that map from R3 to R1, there are 6 ways to set up the iterated integral. And some of you might be thinking that, wait, where does the 6 come from? 6 is 3 factorial. And the two-way is 2 factorial. So therefore, you can see that for function map from R4 to R, now we increase the number of ways to set up the integral by factorial, and therefore increase really fast. As a matter of fact, for R4 to R, there are 24 ways to set up the iterated integral, and we are not going to go through all 24 ways. Okay, and much as I would like to, there's just way too many. But I would like to explore the 6 different ways here, so just to show you. So in this case, the integral, a triple integral in this case, over f of x, y, z dv can be in any of the 6 ways. So maybe I'll write out a few of them just to get you the idea. Okay, so one way to do that is to do this. a1 to b1, integral from a2, maybe x to b to x, and then a3xy to b3xy, f of x, y, z, dz, dy, dx. And the reason why I know that's the way because of the limit. Since the first innermost limit have x and y in it, therefore indicate that it has to be represent a variable that's not x and y, and since we only have x, y, and z, so therefore have to be z. And then the middle integral, because we already take care of z, it cannot be z anymore, but I have the variable x in it, so therefore it has to be y equal to. And then the last one will have to be just constant. So this basically describes the regions B to be gap between these 3 inequality. A sub 3 of xy is between z, between 3 sub 3 of xy. And then y gap between a sub 2 of x and b sub 2 of x. And then x gap between a sub 1 and b sub 1, where they're constant, no variable. So now I can definitely show you a different interpretation. So I can do a sub 1, b sub 1. And then maybe I do a sub 2 of y and b sub 2 of y. And then the last one may be a sub 3 of xy also, and b sub 3 of xy. F of x, y, z. So how does this one work? So notice that the inside still have limit involve x and y, so therefore it should be dz. The middle one involves y, so therefore it has to be dx, because z is gone, and I only have x and y, and since the limit involves y, it cannot be y itself, so it have to be x, and the outside one is y. So therefore this one basically describes the region as a sub 3 of xy is gap between z and b sub 3 of xy. And then the middle one is now x, that gap between a sub 2 of y and b sub 2 of y, and then y is the last one, that gap between a1 and b1. And once again, of course, each of these a1, b1, and a1, a2, a3, b1, b2, b3 are different among each setup. Okay, now I'm going to do one more, and I strongly encourage that you try to do the other 3 on your own. So maybe this one we do something like this. So now by looking at the way the limit is, can you identify the order of integration? So if you want to pause the video and take a minute to think about it, you should, because I'm going to continue. Okay? So if I'm looking at this correctly, I would say this would be dy, dx, dz. Okay? Because the inside most limit have x and y, x and z, so therefore have to be y equal to b3 and y equal to a sub 3. The middle one can have be y equal to, because we already use that, so that leaves x and z, but since the equation involves z, that must be x equal to b sub 2 of z and x equal to a sub 2 of z. And therefore leave the last variable z on the outside most. So therefore in this case, I'm describing the regions B as a sub 3 of xz, a gap between, for y, the gap between. And then the middle one is x, that gap between a sub 2 of z and b sub 2 of z. And then the last variable is z, which gap between a sub 1 and b sub 1. So those are 3 separate examples, and there are 3 other ones, and I strongly recommend that you write them out on your own. Now, interesting thing to note is that I highly unlikely to ask you to actually manipulate the order of integration for something that for a triple integral. It's not that easy to do. You might be asked to do that if I give you some kind of a picture or something, because without visually seeing the picture, it's very hard for you to actually identify which way to set the how to rearrange the order of integration. So but for double integral, you should definitely be able to do, meaning that you should definitely be able to deal with this right here. Okay, so what I want to do next is to give you an example that would and ask you to kind of set the integral two different ways and then to evaluate. And then lastly, I want to talk to you about is what would be some of the advantage and disadvantage of using one way or doing one order of integration versus another. So let's try to evaluate this. Oh, actually, maybe I'll start with this. Let's say given integral from 1 to 2, integral from x squared to x to the third, x dy dx. Maybe I ask you to do the following. A, evaluate this integral. B, how about I sketch the regions of integration? And how about C, rewrite in the opposite order of integration. And I'm not going to ask you to evaluate, but if you want to evaluate it just to see that you get the same answer, you can definitely do that. Evaluate the integral in step C. All right. So let's go ahead and do this integral. It shouldn't be too hard to do. So I'm going to do A first. I'm going to evaluate this integral. So remember what I always like to do, or always ask you to do. So that just helped me visually make sure I don't mess up the substitution. So that will be integral from x from 1 to 2. Integral of x dy is actually xy. Evaluate from y from x squared to x to the third dx. So that's pretty easy. So that just basically integral from x from 1 to 2. X to the fourth minus x to the third dx. And therefore integrate to 1/5 x to the fifth minus 1/4 x to the fourth. Evaluate from x equal to 1 to x equal to 2. So therefore equal to 1/5 2 to the fifth minus 1/4 2 to the fourth. Subtract 1/5 times 1 to the fifth, which is 1, minus 1/4 1 to the fourth, which is 1. So therefore it's 1/4. So let's see. So that comes up to be 32 over 5 minus 2 to the fourth over 1/4 is like 2 squared, which is 4, minus 1/5 plus 1/4. So that would come out to be, let's see, so look like the common denominator is 20. So that's times 4, which is 128, minus 80, minus 4, plus 5. So seem to me that would be 48 minus 4 is 44, plus 5 is 49. So seem to me that the answer is 49 over 20. Hopefully I didn't make a mistake. Now we can definitely sketch the region of integration. So that's actually not too bad to do either. So it seems to me that based on the way the limit is set up, which is this. Oops. That kind of tell me that the region of integration have to be kept between y go between x squared and x to the third, and then x go between 1 and 2. So therefore, we'll probably look something like this. So x squared will probably be something like this. Ooh, actually, you know what? Maybe I will go something like this. And then y to the third actually goes something like this. Okay, you actually have an intersection at the point 1, 1. And then after that, the y to the third will be on top of the x squared. So therefore, that would be where x equal to 1 is. So I'm going to write this down. This is y equal x to the third. This is y equal to x squared. And then x equal to 2 will probably be somewhere over here, where it form this point 2, 4, and this point 2, 8. So it seems to me that little regions right here would be what the regions B will be. Okay. So now this is actually a very good example on what I want to show you next. So now what happens if I want to rewrite this using the other order? So now that actually becomes extremely interesting questions. So here I'm going to just try to magnify this picture a little bit to show you what happened. So this is the point 1, 1. And here is probably the line y equal to x squared. And then here's the line y equal to x to the third. And then here's the strict line x equal to 2, which indicate these 2 points, which is 2, 4, and 2, 8. Now, the interesting thing about this is the following. If I look at this region B right here, notice that B can easily be described by using these two inequalities. It has a top curve, a bottom curve, and then it kind of gets between two x value. Now, the reason why I say that is because the following. If you imagine you try to color in this regions B, when we do dy dx, in this case, this is the order dy dx, because of the y that we go first, it's kind of imagine that we kind of color in these regions using these vertical lines. And notice that every one of these vertical lines gap between x to the third on top and x squared on the bottom. And therefore make it very easy to kind of fill in this entire regions. Okay? The problem is that what we have here is often called a y-simple regions. Because it's easy for me to kind of color in the regions using two curve in y, then just coloring from an x value to another x value. That's called y-simple region. The problem here is the following. If I try to describe the same exact regions, okay, but using dx first, then dy, I run into a major issue. It doesn't mean that we cannot do it. It just means that we have a problem. So I'll show you what the problem is. So here's the same exact regions B. And now instead, I'm going to try to describe these regions B using x inequality first and then y. And now I run into a problem. The problem is the following. So because I'm doing x first then y, I'm kind of using the integral dx dy. And it become a problem because of what I'm going to try to do. This would indicate kind of similar to me kind of fill in this region using horizontal line. Because I have to first define this region gap between two curves from left to right. And then cap it off between top and bottom using horizontal line. So remember, this is basically this way right here. Oh wow, we did a lot. Right here, where you have to define two curves, one on the left, one on the right, and then we have two horizontal lines that gap box in the regions. The problem here is the following. If I were to try to do that, I notice I have a major problem. And the problem is the following. If I start drawing horizontal line to define the two curves that gap between, notice that this is good, 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 until I get to this one point. all this red line a gap between x equal to 2 and the curve y equal to x to the third or x equal to cube root of y. But as soon as I pass this point 2, 4, what happened? What happened is that now my line no longer gap between x equal to 2, but instead it now gap between the line x equal to cube root of y and x equal to square root of y. And so what does that mean is that in this case, this graph is not x simple. Because if I want to do dx first, I actually have to split my regions into 2 in order to properly describe this entire region correctly. Meaning, I cannot actually do this as one single set of inequality, but instead what I need to do is now define B into B1 and B2 and define B to be a union between B1 and B2 without any overlap. And I can now define B1 to be the following. X have to gap between cube root of y and 2, and y have to gap between 4 and 8. So go from 4 to 8 on the y. The region they want to define is gap between the curve cube root of y and x equal to 2. And now I'm going to define B2. B2 would now be gap between x, go between cube root of y to square root, well actually I don't need the 2 if it's square root of y. And y would get between 1 to 4. What is the ramification of splitting the regions? Meaning now in order to evaluate this integral, I actually have to do 2 separate integral. Meaning now I can define my single integral. This integral would actually have to equal to the following. And I'm going to leave it up to you to evaluate the integral if you want to. It might be a little, that actually shouldn't be too hard to do. You just have to do 2 of them. So therefore indicate that this one single integral using dy then dx would actually have to equal to the sum of these 2 integrals. So that presents something that you have to consider when you have to set up a Riemann integral is the regions of integration, x simple or y simple, or there is a third category called xy simple, meaning that you can do either one and it will be okay. Is there a region that's not xy simple? Yes. Those are the toughest one because regardless which way you choose, you're going to have to separate it into multiple pieces. Okay, so therefore that becomes a consideration in what you choose, the order of integration. Now, obviously, if you're looking at what we have on the screen, it makes sense that doing 1 integral is better than doing 2. So is there a reason why you want to do 2 integral? Well, no, because 2 integral is definitely harder to do and more work. But one thing that you do also have to take into consideration is how hard the integration is. If doing 1 integral result in a very difficult integration process, then you might be forced to do multiple of them. hoping that the multiple integral, even though you do more integrations, but the integration is easier to do. So it really depends. So there's a balance between those two things. And it really requires you to see a lot of this question to realize like which way is the better way to go. Trust me, sometimes it still surprises me when I try to set up the integral and thinking like, oh, well, I'll just do 1 instead of 2 and then find out that I get stuck. Okay, so it happened to me too, and I have done a lot more of these than you do. So keep that in mind when you're doing problem. Try to pay attention to when you notice something or when you did a problem and you find out, oh wow, it didn't work out. Then you might want to look up or pay attention to some of the detail of that problem so that you can spot them next time when you see something similar. All right, this actually concludes our 7.1. So most likely we're going to have a test after this, and then we'll move on to 7.3 briefly, and 7.4 is like 6.5. There's no really homework assignment or anything, just a couple theorems that I want to point out to you, and then 7.4 will be the big section that we have to go through in chapter 7. All right, that's it for today for this video, and I'll talk to you guys soon. Okay, bye bye.